In 2018, two scientists sat down to write a paper that would haunt the scientific community for years to come. Gavin Schmidt, a climate modeler at NASA's Goddard Institute for Space Studies, and Adam Frank, an astrophysicist at the University of Rochester, were not trying to prove anything extreme. They were asking a question, a simple, terrifying question that nobody had seriously considered before. Could we find evidence of an industrial civilization in Earth's rock record if that civilization existed millions of years before humans? The question sounds like science fiction. It sounds like the start of a conspiracy documentary or a late-night talk caused by too much coffee and not enough sleep. But Schmidt and Frank were not outsiders. They were respected scientists with strong credentials, and they were completely serious. They called their thought experiment the Silurian Hypothesis, named after an episode of the British TV show Doctor Who, featuring intelligent reptilian humanoids who ruled Earth hundreds of millions of years ago. The name was tongue-in-cheek, a nod to science fiction, but the science behind it was careful and unsettling. If you enjoy exploring the universe's deepest secrets and questioning everything you thought you knew about reality, hit that subscribe button. We're going deep tonight. Prepare yourselves. The impossible question is waiting in the geological record. The paper landed like a bomb in the world of astrobiology and climate science, not because Schmidt and Frank claimed to have found evidence of ancient civilizations. They clearly stated they doubted any such civilization had existed, but they had done something more unsettling. They showed that we probably would not be able to tell the difference between a natural climate event and one caused by industrial activity if that activity happened tens of millions of years ago. Think about that carefully. Right now, at this very moment, human civilization is changing the chemistry of Earth's atmosphere at a rate never seen in the geological record. We are burning fossil fuels, releasing carbon that has been buried for hundreds of millions of years. We are creating synthetic chemicals that have never existed in nature. We are dumping plastic into the oceans at a rate that will leave a permanent layer in the sedimentary record. We are changing the isotope ratios of elements in ways that future scientists will be able to detect millions of years from now. Our fingerprints are being pressed into stone. But here comes the twist that keeps scientists awake at night. When Schmidt and Frank looked back through Earth's history, they found events that looked disturbingly similar to what we are doing now. Temperature spikes, carbon isotope problems, mass extinctions, ocean chemistry changes, events that seem to have no clear natural explanation, or at least no explanation that fully matched the data. The most striking example happened 56 million years ago during an event called the Paleocene Eocene Thermal Maximum. Earth's temperature jumped by up to 15 degrees F. Carbon isotopes shifted dramatically. Species went extinct in the deep ocean. The event lasted for hundreds of thousands of years, leaving clear markers in the geological record, and nobody knows exactly what caused it. Volcanoes are the usual suspect. Massive eruptions can release huge amounts of carbon dioxide. Methane trapped in frozen sediments can be released when oceans warm, creating a runaway greenhouse effect. These natural mechanisms exist and they are powerful, but the chemical signatures do not match perfectly. Something happened 56 million years ago that changed the planet, and the explanation is still incomplete. Schmidt and Frank were not suggesting that ancient reptile people caused the Paleocene-Eocene Thermal Maximum. They were making a more subtle and more important point. If an industrial civilization had existed during that time, burning fossil fuels for a few 100,000 years before collapsing, the geological signature would look almost identical to what we observe. We would see the same carbon isotope shifts, the same temperature spikes, the same extinction patterns, and we would have no way to separate it from a natural event because the time scales blur together and the physical evidence gets destroyed. This realization opens a door that cannot be closed. For all of human history, we have assumed we were first. First to build cities, first to create technology, first to change the planet on a global scale. This assumption runs so deep that we rarely question it. But Schmidt and Frank showed that our assumption might be based not on evidence, but on the lack of evidence we would never expect to find in the first place. The geological record is not a complete archive. It is a broken, incomplete, heavily edited version of Earth's history with most pages missing completely. Consider what we know about the fossil record. Paleontologists estimate that fossilization is an incredibly rare event. An animal dies, gets buried quickly under the right conditions, And over millions of years, minerals replaced the organic material, preserving the shape. The vast majority of organisms that have ever lived left no trace. They decomposed, got eaten, got crushed, got dissolved. Finding a fossil is like finding a single photograph in an archive that should contain billions. Now think about technological artifacts. How long does a building last? A few thousand years if you are lucky and it is in a dry climate. A few centuries if it is in a wet environment. Erosion, weathering, plants, and geological processes tear everything down. The oldest large-scale surface on Earth found in the Negev Desert is only 1.8 million years old. Everything older than that has been ground down, pushed down into the mantle, covered by new rock layers or otherwise erased. If you go back beyond about 2.6 million years ago, the beginning of what geologists call the Quaternary period, you are looking at a world where no direct evidence of cities or artifacts could possibly remain on the surface. Everything would have turned to dust. This creates a basic problem for finding ancient civilizations. Humans in our current form, Homo sapiens, have existed for only about 300,000 years. We have been building cities for maybe 10,000 years. We have been industrial for about 300 years. That is a tiny piece of Earth's history, a brief moment in geological terms. If another species evolved intelligence, developed technology, built an industrial civilization, and then collapsed all within a period of a few 100,000 years, say 100 million years ago, we would almost certainly find nothing. No buildings, no roads, no statues, no complex artifacts. The surface would have recycled itself dozens of times. Tectonic plates would have ground evidence into nothing. The only traces would be subtle chemical signatures buried deep in sedimentary layers. Signatures that might look natural to an untrained eye. Schmidt and Frank were not claiming this happened. They were showing that if it happened, we might never know. The implications reach far beyond Earth. Astrobiologists spend huge effort searching for signs of intelligent life on other planets. The famous Drake equation tries to estimate how many communicating civilizations might exist in our galaxy at any given time. One of the key variables in that equation is the lifespan of a technological civilization. How long does a species stay detectable before it either destroys itself, changes into something we cannot recognize, or simply goes quiet? If industrial civilizations tend to be short-lived, collapsing after just a few 100,000 years, then the Drake equation produces very different results. The galaxy might be full of dead civilizations, worlds where intelligence rose and fell millions of years ago, leaving only faint chemical traces that would be invisible from space. We might be surrounded by the ghosts of countless industrial ages, and we would never know because we are looking for the wrong things. Here on Earth, the question becomes even more specific. Complex life, meaning life more advanced than single-celled organisms, has existed for at least 400 million years. That is 400 million years of opportunity. Thousands of species have evolved during that time. Some developed remarkable intelligence. Cephalopods like octopuses show problem-solving abilities that rival some mammals. Certain birds use tools and teach their young. Dolphins have complex social structures and communication. None of these species developed industrial civilization, but they show that intelligence can evolve when the right pressures exist. So why assume humans are the only species that ever crossed the line into technology? The answer has always seemed obvious. We do not see any evidence of previous civilizations. No ruins, no artifacts, no fossil cities. The lack of evidence has been treated like proof that nothing was there. But Schmidt and Frank showed that lack of evidence means nothing when the evidence cannot survive. The paper did something unusual for a scientific publication. It started by admitting its own conclusion up front. The authors wrote that they strongly doubted any previous industrial civilization had existed before humans. This was not a claim that ancient aliens built the pyramids or that lizard people ruled the Cretaceous period. This was a formal thought experiment designed to explore the limits of our knowledge. By asking the question clearly and working through what evidence might look like, they revealed just how little we actually know about Earth's deep history. The response from the scientific community was mixed. Some researchers welcomed the hypothesis as a useful way to think about detectability across civilization time scales. Others dismissed it as too speculative, pointing out that extraordinary claims require extraordinary evidence, and there was no evidence to study. But a small group found themselves deeply unsettled by the implications. If we cannot detect a previous civilization that might have existed 100 million years ago, what does that say about our own civilization's lifespan? We are leaving traces. Yes, carbon isotope spikes, plastic layers, radioactive elements from nuclear testing. Future geologists, if they exist, will see a clear boundary in the rock record marking the Anthropocene, the age of humans. But what if that boundary is very thin? What if industrial civilizations almost always collapse quickly, burning through their resources, destabilizing their climate, and vanishing in geological terms almost as soon as they appear? The Silurian Hypothesis forces us to face uncomfortable possibilities about the nature of technological progress and its sustainability. Every major climate event in Earth's past has been explained as natural causes. Volcanic eruptions, asteroid impacts, changes in ocean circulation, variations in Earth's orbit. These explanations are supported by evidence and they make sense, but Schmidt and Frank introduced doubt. How many of these events have we studied closely enough to rule out an industrial cause? The answer is almost none. The method for detecting ancient industrial activity does not really exist yet. Geologists are not trained to look for signs of past civilizations in the rock record, because the assumption has always been that no such civilizations existed. The tools and techniques for identifying synthetic chemicals, unusual isotope ratios, and strange sediment patterns exist, but they have not been used systematically to answer the question of detectability. This means we are operating in deep ignorance. We have studied maybe 1% of Earth's geological history in detail. The rest remains unexplored territory where anything could be hiding. The Silurian Hypothesis has another side that makes it especially important now. Climate change is the defining challenge of our era. We are running a massive, uncontrolled experiment on the only planet we have, releasing carbon at a rate never seen in Earth's history. The consequences are becoming visible. Rising temperatures, melting ice, changing weather patterns, ocean acidification. We are living through the early stages of a planetary transformation, and we have no idea how it ends. But what if this has happened before? Not the natural climate cycles that Earth has gone through throughout its history, but an industrial civilization pushing its own planet past a tipping point it could not recover from. If we found evidence that a previous species did exactly what we are doing now and collapsed because of it, it would be the most important discovery in human history. It would be a warning written in stone, a message from the deep past telling us that the path we are on leads to extinction. The problem is that we might not recognize the message even if we found it. The signals would be subtle, buried in technical data, easy to explain away as natural variation. Only by searching specifically for industrial signatures could we hope to identify them. And even then, the evidence might be unclear. This is the nightmare scenario that haunts researchers who take the Silurian Hypothesis seriously. We might be repeating a mistake that has already destroyed civilizations before us, and we would have no way of knowing until it was too late. Schmidt and Frank's paper has inspired a new field of research. A handful of scientists are now looking at ancient climate events with fresh eyes, searching for patterns that might suggest industrial activity. They are developing new techniques for detecting synthetic molecules in ancient sediments. They are cataloging the kinds of signatures that advanced technology would leave behind. The work is slow and controversial, but it represents a basic shift in how we think about Earth's history. We are no longer assuming we were first. We are testing that assumption. The results so far have been inconclusive, which is exactly what you would expect if ancient civilizations either did not exist or left traces too subtle to detect with today's methods. But the absence of clear evidence does not close the question. It leaves it open, hanging in the air like a challenge. Think about how bold the question is. We are asking whether intelligence has evolved on Earth more than once, whether the long history of life on this planet includes chapters we know nothing about, whether the rock beneath our feet contains secrets that would rewrite everything. This is not empty guessing. This is science pushing against the edges of what can be known, admitting the limits of our knowledge and refusing to accept comfortable assumptions without testing them. The Silurian Hypothesis shows something deep about the scientific method. It starts with a question that most people would dismiss as ridiculous. Then it uses careful analysis to figure out what evidence would look like if the ridiculous thing were true. Then it goes looking for that evidence, fully ready to find nothing, but also fully ready to be wrong about basic assumptions. This is how science moves forward. Not by clinging to what we think we know, but by questioning everything and following the evidence wherever it leads. Here is what we know for sure. Earth is 4.6 billion years old. Life began at least 3.7 billion years ago. Complex multicellular life appeared around 600 million years ago. Intelligence has evolved multiple times in multiple lineages. Humans are not the only smart species, just the only one currently building cities and rockets. The timeline is vast, the opportunities are many, and the geological record is incomplete. Everything else is inference and assumption. We assume we were first because we do not see evidence to the contrary. But as Schmidt and Frank showed, that evidence might not exist in a form we can recognize, or it might exist, and we simply have not looked in the right places with the right tools. The door is open now. The question has been asked formally in peer-reviewed scientific literature. It cannot be unasked. Somewhere in the geological record, buried in ancient rock layers or scattered across the surfaces of the Moon and Mars where erosion cannot erase it, there might be evidence that we are not the first. That intelligence has risen before. That industrial civilization has happened before. That the crisis we face now is not unprecedented, but instead the likely fate of any species that discovers fire and fossil fuels faster than it discovers wisdom and restraint. Or maybe the evidence is not there because it never happened. Maybe we really are first, unique in Earth's long history, the only species to ever build a global technological civilization. But we cannot know which answer is true until we look. And looking requires us to face uncomfortable possibilities about both the past and the future. The Silurian Hypothesis is not really about ancient reptile civilizations or science fiction stories. It is about humility, about realizing how much we do not know, about understanding that absence of evidence is not the same as evidence of absence when the evidence could not possibly have survived. It is about taking seriously the idea that we might be walking a path others have walked before, a path that leads somewhere we do not want to go. The paper ends with a call for more research. Schmidt and Frank listed specific areas where research could improve our limits on the hypothesis. Better surveys of ancient sediments looking for unusual chemical signatures. More detailed models of how industrial byproducts would last over geological time scales. Examination of the Moon and Mars for possible artifacts from spacefaring precursor civilizations. These recommendations have mostly not been followed, not because they are not scientifically solid, but because funding for speculative research is limited, and the chance of finding anything seems low. But probability is a strange thing when dealing with unique events. The probability that intelligent life would evolve on Earth was probably very low. Yet here we are. Low probability events happen constantly when you have billions of years to work with. The question is not whether previous civilizations were likely, but whether they were possible, and if possible, whether we would know. As you read this, carbon dioxide levels in the atmosphere continue rising. Glaciers continue melting. Species continue going extinct at rates not seen since the last major mass extinction event. We are in the middle of our own planetary transformation, and the outcome remains uncertain. Future geologists, if they exist, will see our signature clearly in the rock record. A thin layer of plastic and concrete and radioactive isotopes marking the moment when one species briefly dominated the planet before something happened. What that something will be depends on choices we make. Now, the Silurian Hypothesis suggests that this moment, this shift from pre-industrial to whatever comes next, might be a universal challenge for technological civilizations, a great filter that few species pass through successfully. If we are the first to face it, we have no guidance, no warnings, no examples to learn from. But if we are not the first, if others have stood where we stand now and made the choices we are about to make, then the geological record might contain the most important information our species will ever find. The truth about what happens next. The impossible question has been asked. The door has been opened. What lies beyond it is unknown, waiting in the deep time of Earth's history, hidden in chemical signatures and isotope anomalies and gaps in the fossil record. We might find nothing, we might find everything, but we will never know until we look. And looking requires us to question the basic assumption that has shaped human thought for all of recorded history. The assumption that we are first, that we are unique, that the planet was waiting for us to arrive and claim it. Maybe that assumption is correct. Or maybe we are just the latest chapter in a much longer story, one that has been told before and will be told again. The Silurian Hypothesis does not answer that question. It simply forces us to ask it seriously for the first time. Earth keeps no permanent records. The planet you stand on right now is not the same planet that existed 100 million years ago. Not metaphorically, literally. The ground beneath your feet is newer than the dinosaurs. Most of it is newer than the mammals. Some of it is newer than human civilization. The surface of Earth recycles itself constantly through processes so powerful and so slow that we barely notice them happening. But over millions of years, these processes erase everything. Cities vanish, mountains dissolve, entire continents get swallowed into the mantle and pushed back up as new crust. The geological amnesia is total and merciless. Plate tectonics is the main engine of destruction. The crust of Earth floats on a layer of semi-molten rock called the asthenosphere. This layer flows like honey, driven by heat from the planet's core. The crust itself is broken into huge plates that drift across the surface at rates of a few centimeters per year. Where plates collide, one gets forced under the other in a process called subduction. The sinking plate melts back into the mantle, taking everything on its surface with it. Ocean crust gets completely recycled every 170 million years or so. Nothing on the ocean floor is older than that. Every single rock, every sediment layer, every structure that might have existed has been destroyed and remade. Continental crust lasts longer, but not forever. Mountains rise where plates collide, then erosion tears them down, grain by grain. Rain, wind, ice, and rivers work non-stop to flatten the land. The Appalachian Mountains once stood as tall as the Himalayas. Now they are worn stumps, reduced to gentle hills by 300 million years of weathering. The rock that made up their peaks is gone, washed into the ocean, buried under new sediments, or subducted into the mantle. If a city had existed on those ancient peaks, no trace would remain. The mountains themselves are barely recognizable. Consider what this means for finding ancient artifacts. A building made of stone might last 10,000 years if conditions are perfect. The Great Pyramid of Giza is less than 5,000 years old, and already showing serious erosion, even though it is in one of the driest climates on Earth. In a temperate zone with regular rainfall, that pyramid would become unrecognizable rubble in 20,000 years. In a tropical rainforest with heavy rain and aggressive plants, it would disappear even faster. By 100,000 years, nothing recognizable would remain except maybe some unusual concentrations of cut stone buried under meters of soil. By 1 million years, even those traces would be scattered, broken, dissolved. By 10 million years, the landscape itself would have changed so much that finding anything would be impossible. Metal artifacts do even worse. Iron rusts and crumbles within centuries when exposed to air and water. Even stainless steel breaks down eventually. Aluminum oxidizes. Copper forms a patina but keeps corroding. Gold and platinum survive, but they are too valuable to leave lying around. Any civilization would recycle precious metals constantly. The only metal traces that might last would be in concentrated ore deposits where mining pulled material out. But even those signatures could be mistaken for natural mineral concentrations. Finding a suspiciously rich ore deposit tells you nothing about whether something intelligent mined similar deposits nearby. Concrete and asphalt break down surprisingly fast. Modern roads start falling apart within decades without maintenance. The concrete used in ancient Roman structures has certain mineral mixes that make it unusually durable. But even Roman concrete breaks down with enough time. By 1 million years, a highway system would be completely gone. Not hidden under plants, not buried under sediment. Gone. Broken into sand-sized particles and scattered across the landscape by rivers and wind. The molecular structure of the concrete would stay briefly as calcium carbonate deposits that look exactly like natural limestone. Then even that signature fades as the material gets built into new rocks through diagenesis, a process by which sediments turn into solid stone. Plastic creates a different problem. Modern civilization makes huge amounts of plastic that resist breaking down. Microplastics collect in ocean sediments and will probably stay detectable for millions of years as a distinct layer in the geological record. Future scientists studying rock cores from our era will find plastic particles throughout sediments laid down between roughly 1950 and whenever our civilization ends. This layer will be thin, maybe only a few centimeters thick after compression, but distinctive. However, telling artificial polymers apart from natural organic compounds in ancient rocks is not simple. Petroleum exists naturally. Complex hydrocarbons form through geological processes. Unless you are specifically searching for synthetic polymers and using advanced chemical analysis, you might miss the signature completely or dismiss it as contamination. The oldest exposed bedrock on Earth's surface dates back only about 1.8 million years, found in the Negev desert where extremely dry conditions reduce erosion. Everywhere else, the surface is younger, much younger. Most of what you see is less than 100,000 years old. Walk through a forest, and the soil beneath your feet formed within the last few thousand years from decomposed plant matter and weathered rock. The bedrock underneath might be ancient, but the surface is new. This creates a basic problem. If you want to find evidence of a civilization that existed 50 million years ago, you cannot look at the surface. You have to drill down into sedimentary rocks that formed during that time period and were later buried under younger deposits. You have to find places where geological uplift or erosion has exposed those ancient layers. And then you have to analyze them with tools designed to detect industrial signatures that nobody has searched for before. Sedimentary rocks offer the best chance of preservation. These rocks form when particles settle out of water or air and get compressed into stone over millions of years. The process preserves chemical signatures surprisingly well. Fossils form in sedimentary rocks. Climate records get locked into ice cores and ocean sediments. If an ancient civilization left traces, sedimentary layers would be where to find them. But reaching those layers is hard. Most sedimentary rocks are buried under kilometers of younger material or submerged beneath oceans. The few places where ancient sediments are exposed and reachable are a tiny fraction of Earth's surface. We have studied even less of that tiny fraction in detail. Ocean sediments build up slowly, usually a few centimeters per 1,000 years. A civilization lasting 100,000 years might leave signatures spread across a few meters of sediment. After that sediment gets compressed into rock, the signature layer could be just centimeters thick. Finding it requires knowing exactly where and when to look. The ocean floor older than 170 million years does not exist anymore because of subduction, which removes more than half of Earth's possible sedimentary record. The deep ocean basins we see today are all geologically young. Any evidence older than 170 million years must be found in rocks that formed in ancient oceans and were later pushed onto continental crust before the ocean floor got recycled. Lake sediments preserve records differently. Lakes fill with sediment much faster than oceans, creating thick deposits in relatively short time periods. Ancient lake beds sometimes survive on continents, protected from subduction by the stability of continental crust. These places are gold mines for paleontology because they preserve detailed records of local environments. But lakes are temporary in geological terms. They fill with sediment and become plains. They drain when river channels shift. They disappear when climate changes. A lake that existed 100 million years ago in what is now desert might have preserved amazing detail about that time period. But finding it requires knowing where ancient lakes were, and then locating deposits that have not been destroyed by later erosion or tectonic activity. The fossil record shows just how incomplete our knowledge is. Paleontologists estimate that we have found fossils representing less than 1% of all species that ever existed. Fossilization requires special conditions. An organism must die in a place where it gets buried quickly before scavengers and decay destroy it. The burial environment must be low in oxygen to slow decay. Minerals must seep into the remains and replace organic material with stone. Then the fossil must survive millions of years without being crushed, melted, or dissolved. Finally, erosion or digging must expose the fossil at a time and place where someone can find it. Each step in this process filters out most possible fossils. The result is a record so thin that entire groups of organisms might leave no trace at all. Now consider technological artifacts instead of biological organisms. A bone has a better chance of fossilizing than a smartphone. Organic material readily gets replaced by minerals. Calcium phosphate in bones gives a template for minerals to follow. Silicon and metal do not fossilize the same way. They corrode and crumble into unrecognizable debris. A fossilized dinosaur bone still looks like a bone even after 100 million years. A fossilized computer would not look like anything recognizable. It would be a stain in the rock, a slight discoloration, maybe an unusual concentration of rare earth elements if you tested it chemically. Without knowing what to look for, you would never identify it as artificial. Even if artifacts somehow survived intact, finding them would be nearly impossible. Human archaeology struggles to find sites only a few thousand years old. Ancient cities get discovered by accident when construction crews dig foundations or farmers plow fields. Deliberate searches using ground-penetrating radar and satellite imagery improve success rates, but huge areas remain unexplored. Now multiply that challenge by a factor of thousands. Instead of searching for cities buried under a few meters of soil, you are searching for evidence buried under kilometers of rock. Instead of artifacts made last millennium, you want artifacts made 100 million years ago that have been crushed, heated, and chemically changed beyond recognition. The odds of success approach zero. This is why the absence of evidence means nothing. We have not found ruins of ancient prehuman civilizations because we would not expect to find ruins even if they existed. The geological processes on Earth destroy evidence faster than we can search for it. The planet is constantly rewriting its surface, grinding old material back into the mantle, and creating new crust from volcanic activity. This cycle has repeated countless times over billions of years. Anything on the surface more than a few million years old is gone. The only traces that last are subtle chemical signatures in rocks that formed during the right time period, survived subduction and erosion, and happen to be accessible for study today. That is a very narrow window. The implications are shocking. Earth could have hosted dozens of industrial civilizations over the past 400 million years, and we would probably never know. Each one could have risen, flourished for a few 100,000 years, and collapsed without leaving detectable traces. The geological amnesia would erase them completely, leaving at most some unclear chemical anomalies that could be explained as natural variation. We assume we are first because the planet shows no clear evidence of earlier civilizations. But the planet would show no clear evidence even if earlier civilizations existed. The assumption is based on absence, and absence proves nothing when the evidence cannot survive. Future archaeologists studying our era will face similar problems. If human civilization collapsed tomorrow and another intelligent species evolved 50 million years from now, what would they find? They would see a thin layer of unusual sediment marking our time period. Higher carbon isotope ratios from burning fossil fuels, plastic microparticles throughout ocean deposits, traces of radioactive isotopes from nuclear testing, unusual concentrations of metals in certain places where cities once stood. But they would find no buildings, no roads, no recognizable artifacts, just chemical fingerprints and subtle signatures that might or might not be blamed on intelligence, depending on how carefully they looked and what assumptions guided their analysis. We are leaving traces, yes, but those traces will be unclear and easy to miss unless someone searches specifically for them. The geological amnesia is total. Earth remembers nothing directly. It destroys buildings and artifacts and turns them into anonymous sediment. The only things that survive are processes recorded in chemistry, isotope ratios, trace elements, unusual molecular compounds. These signatures last for tens of millions of years if the rocks containing them avoid destruction. But understanding those signatures requires knowing what to look for, and we have only recently started asking the right questions. The next chapters will explore what traces might exist, where they could be found, and why the search is more urgent than most scientists realize. The planet may be trying to warn us about something that happened before. We just have to learn how to read the message written in stone. 350 million years ago, Earth was almost unrecognizable compared to today. The continents were arranged differently. Most of them were joining into a supercontinent called Pangaea that was still forming. The climate was warm and humid across much of the planet, and forests. Vast forests unlike anything that exists now covered the land. These were not the forests of today with their diverse mix of flowering plants and evergreens. These were the coal forests of the Carboniferous period, dominated by giant club mosses, horsetails, and tree ferns that grew to heights of 30 meters. The trees had shallow root systems and grew densely packed in swamps that stretched for hundreds of kilometers. When they died, they fell into oxygen-poor water and did not decay. Instead, they built up layer upon layer, eventually forming the massive coal deposits that power our civilization today. Here is what makes the Carboniferous period especially interesting for the Silurian hypothesis. This was the first time in Earth's history when enough fossil carbon existed to fuel an industrial civilization. The coal forests had been growing and dying and building up for tens of millions of years, burying huge amounts of carbon underground. Any species that evolved intelligence during or after this period would have had access to concentrated energy sources similar to what humans discovered in the 18th century. The temptation is to imagine some species stumbling on this resource, learning to burn it for heat and power, and starting their own industrial revolution hundreds of millions of years before humans appeared. The chemistry was right. The fuel was there. But was the biology ready? Intelligence is not guaranteed to evolve just because conditions allow it. The Carboniferous period had some remarkable creatures, but none seem to have been likely candidates for developing technology. The largest land animals were arthropods. Giant millipedes stretched 2 meters long. Dragonflies with 70-centimeter wingspans ruled the skies. Scorpions grew to frightening sizes. These creatures thrived in the high-oxygen atmosphere of the period, sometimes reaching 35% compared to today's 21%. But arthropods have basic limits. Their exoskeletons limit how large they can grow on land, and their nervous systems are spread out and fairly simple compared to vertebrates. No arthropod has ever shown the level of intelligence needed for tool use and abstract reasoning. Amphibians were just starting to diversify during this time. Early tetrapods, the first four-limbed vertebrates to live on land, were spreading into land environments and adapting to life outside the water. Some grew quite large, becoming top predators in swamp ecosystems. But these animals were still very primitive compared to later vertebrates. Their brains were small, their behavior patterns simple, and their need for water to reproduce was limiting. They were not candidates for intelligence in any meaningful sense. Reptiles would not appear until later in the Carboniferous, and even they would take millions of years to diversify into forms capable of complex behavior. So the Carboniferous creates a paradox. The needed resource existed for the first time, but no animal capable of using it had evolved yet. This timing mismatch is important. It suggests that having fossil fuels available is not enough. A species needs certain traits to use them. Hands able to manipulate, the ability to start fire, social structures that pass knowledge across generations, abstract reasoning to connect cause and effect, and most importantly, the right selective pressures to push the evolution of those traits. None of these existed during the Carboniferous, at least not in any form we can detect from the fossil record. But the fossil record is incomplete. We have fossils of the most common and easiest to preserve animals from this period. We have the giant arthropods because they left clear impressions. We have amphibian bones because bones fossilize fairly well. What we do not have is a complete list of every species that lived during the 60 million years of the Carboniferous period. Rare species, small species, species that lived in places where fossilization was unlikely, could have existed without leaving traces. This creates an opening, admittedly a small one, for speculation. Could some unknown lineage have evolved intelligence during this time? Could it have discovered fire and coal, and built a civilization that lasted briefly before collapsing and disappearing from the fossil record? The honest answer is almost certainly not. But the possibility cannot be fully removed. If such a civilization existed, it would have been very different from anything we can imagine based on modern animals. Perhaps an arthropod lineage that somehow overcame the nervous system limits of their body plan. Perhaps an unknown group of vertebrates that left no fossils. Perhaps something else entirely. Some evolutionary experiment that succeeded briefly and then went extinct without descendants. The evidence for this is zero. The plausibility is near zero. But zero evidence is not the same as disproof when evidence would not be expected to survive anyway. What we can say with confidence is that if a Carboniferous civilization existed, it was not widespread or long-lasting. The chemistry of the geological record shows no signs of massive industrial activity during this period. Carbon isotopes behave as expected for natural processes. There are no unusual spikes in metals or synthetic compounds. The climate stayed stable by the standards of geological change. Whatever happened during the Carboniferous followed natural patterns, but natural patterns can sometimes hide small-scale events. A civilization lasting 10,000 years on a single continent would leave almost no detectable trace in the global geological record. The signal would be lost in the noise of natural variation. Consider what a Carboniferous industrial revolution would have looked like. The species would have found coal by accident, maybe noticing that certain black rocks burned hotter and longer than wood. They would have started using coal for heating, then for metalworking as they discovered ores. Copper, tin, and iron existed then as they do now, waiting to be mined and refined. A technological species could have developed Bronze Age and Iron Age technology using the same resources humans later used. They could have built cities near coal deposits, mined the seams systematically, and created an industrial system that lasted for thousands or tens of thousands of years. But then what? Every industrial civilization faces the same problem. Limited resources get used up. Environmental impacts build up. Climate starts changing as carbon dioxide from burning fuel builds up in the atmosphere. A carboniferous civilization would eventually face an energy crisis as easy-to-reach coal deposits ran out. They would have experienced climate instability as their emissions changed the atmosphere's chemistry. And because they rose during a time when global temperatures were already high, any extra warming would have pushed ecosystems past critical tipping points. The collapse would have been unavoidable and probably fast in geological terms. After collapse, erosion and geological processes would erase the physical evidence, but chemical traces might remain. Unusual carbon isotope ratios in sediments from that era, unusual amounts of soot particles, trace metals in patterns that suggest smelting. These signatures would be subtle and local, easy to miss unless you were looking specifically for them. No one has looked. Geologists studying carboniferous sediments focus on coal formation, climate patterns, and the evolution of early land ecosystems. They are not searching for industrial signatures because the assumption is that no industry existed. This creates a circular problem. We do not search because we assume nothing is there. We assume nothing is there because we have not found anything. But we would only find something if we searched with the right methods and knew what signatures to look for. The Carboniferous period ended about 290 million years ago when the climate shifted toward cooler and drier conditions. The great coal swamps dried up and disappeared. The forests changed. Many species went extinct. The door of opportunity closed, at least for a while. But the coal stayed underground, buried and compressed, waiting to be found by whatever species evolved the ability to use it. That species turned out to be humans, arriving roughly 289.7 million years later. We found the coal, burned it eagerly, and now face the consequences of that choice. If another species had found it first, they would have faced the same consequences. The physics and chemistry cannot be avoided. This raises a disturbing question. Is industrial civilization naturally self-limiting? Does finding fossil fuels inevitably lead to rapid technological growth followed by environmental collapse? The pattern seems universal. Concentrated energy sources enable rapid expansion. Rapid expansion uses up resources and destabilizes climate. Destabilization leads to stress in society and collapse. If this pattern holds, then any civilization arising during or after the Carboniferous would face the same path. They would burn the ancient sunlight stored in coal and oil. They would release carbon that had been locked away for millions of years. They would change the atmosphere faster than ecosystems could adapt, and then they would collapse, leaving only faint chemical traces in the rocks. The Carboniferous temptation is not really about that specific time period. It is about the moment in Earth's history when fossil fuels first became available in large enough quantities to power industrial development. That moment happened 350 million years ago and has continued ever since. Every later period has had coal, oil, and natural gas deposits formed from ancient organic matter. The Permian had fossil fuels. The Triassic had fossil fuels. The Jurassic and Cretaceous both had fossil fuels forming in their swamps and oceans. The Cenozoic added oil deposits from marine organisms. Any intelligent species arising during any of these periods would have faced the same temptation humans faced. Easy energy, rapid progress, unforeseen consequences. We know intelligence evolved multiple times in Earth's history after the Carboniferous. Dinosaurs included species with large brains compared to body size and complex social behaviors. Some theropods showed problem-solving abilities. Birds, which are dinosaurs, show remarkable intelligence today. Crows use tools, parrots solve puzzles, ravens plan for the future. Marine reptiles during the Mesozoic era might have been intelligent in ways we cannot detect from fossils. Cetaceans, which evolved later, clearly have sophisticated thinking. Elephants, primates, and many other mammal groups show advanced thinking abilities. Intelligence keeps evolving because it helps survival. But none of these intelligent species, except humans, developed technology that required fossil fuels. The question is why? What makes humans different? The usual answer is our special combination of traits. Upright posture, freeing hands for tool use, large brains capable of abstract reasoning, complex language for sharing knowledge, social systems that support specialization and cooperation, and fire-starting ability that expanded our diet and provided warmth. All these factors combined in a unique way that let us bootstrap from stone tools to industrial civilization over a few 100,000 years. But many of these traits are not unique to humans. Other species use tools. Other species have complex communication. Other species live in sophisticated social groups. The difference seems to be one of degree rather than kind. Maybe the real difference is timing and luck. Humans evolved during a time when climate was fairly stable, allowing agriculture to develop. We had hands from our primate ancestry. We lived in environments that gave us many challenges that required clever solutions. We discovered fire early in our evolution and used it for cooking, which changed our nutrition and brain development. One thing led to another, and eventually we discovered coal during a time when we already had the metallurgy skills to use it well. Maybe another species could have followed a similar path during a different time period. Maybe some species did follow that path, and we just have not found the evidence. Or maybe we really are unique, the only species to ever make this particular leap. The Carboniferous period stands as a milestone. It marks the moment when the possibility of industrial civilization became real. Before that time, not enough fossil carbon existed to power long-term industrial activity. After that time, the fuel was always available, waiting for the right species to discover it. We happen to be that species, arriving late on a planet that already had 4 billion years of evolution. But arriving late does not guarantee arriving first. The possibility exists that others came before us, found the coal, burned it, and disappeared. The chemistry cannot rule it out. The physics allows it. The biology remains unclear. We are left with uncertainty and the nagging question of whether the ground beneath our feet holds secrets we have not yet imagined. Right now, at this exact moment, human civilization is writing its signature into the geological record. Future scientists examining rocks from our era will see something never before seen in Earth's 4.6 billion-year history. Not the presence of life, not the existence of intelligence, but the unmistakable chemical fingerprint of an industrial species burning through its planets, stored energy at rates never before achieved. We are running an experiment in real time, creating the very markers that Schmidt and Frank suggested searching for in ancient rocks. Understanding what we are leaving behind tells us exactly what to look for when searching for evidence of previous civilizations. Start with carbon isotopes. Carbon exists in 3 naturally occurring forms. Carbon-12 is the most common, making up about 99% of all carbon. Carbon-13 makes up about 1%. Carbon-14 is radioactive and exists in tiny amounts. These isotopes behave the same in chemical reactions, but living things tend to take in carbon-12 into their tissues because it is slightly lighter and takes slightly less energy to use. When plants photosynthesize, they pull carbon dioxide from the air and build it into sugars and cellulose, and they favor carbon-12 over carbon-13. This creates a distinctive ratio. Organic matter is low in carbon-13 compared to inorganic sources like volcanic emissions or carbonate rocks. Now, here is where it gets interesting. Fossil fuels are the remains of ancient living things. Coal formed from plants. Oil and natural gas formed from marine organisms. All of this organic matter is low in carbon-13 because the original organisms favored carbon-12. When we burn fossil fuels, we are releasing carbon that has been locked underground for hundreds of millions of years. And that carbon carries the isotope signature of ancient life. The carbon dioxide we pump into the atmosphere is noticeably low in carbon-13 compared to natural sources. Atmospheric scientists call this the Suess effect. Named after the chemist Hans Suess, who first identified it in the 1950s, the Suess effect is accelerating. Since the start of the Industrial Revolution, the ratio of carbon-13 to carbon-12 in the atmosphere has shifted in a measurable way. The change is small, only about 2 parts per thousand, but it is detectable with modern instruments, and it is increasing every year. This shift will be permanently recorded in any material that takes in atmospheric carbon during our era. Tree rings show it. Ice cores show it. Ocean sediments show it. Calcium carbonate shells made by marine organisms show it. The isotope signature is everywhere, and it will last for millions of years in rocks that form from sediments deposited today. A geologist studying sedimentary rocks from our time period 50 million years from now would see this isotope anomaly clearly. They would find a layer where carbon-13 suddenly becomes lower compared to the layers around it. The drop would be sharp, happening over a geologically brief interval that matches our few centuries of industrial activity. The pattern would be hard to explain through natural processes. Volcanic eruptions release carbon low in carbon-13, but volcanic carbon has a different signature from organic carbon. Large-scale decay of organic matter could, in theory, produce similar effects, but such decay usually happens gradually, not in a sudden pulse. The isotope fingerprint we are leaving is distinctive and unusual. Temperature proxies will show matching changes. When we measure ancient temperatures, we use several methods. Oxygen isotope ratios in ice cores and marine sediments reveal past temperatures because the ratio changes depending on how much water is locked up in glaciers versus oceans. During cold periods, glaciers grow and preferentially trap oxygen-16, leaving the oceans richer in oxygen-18. During warm periods, glaciers melt and release oxygen-16 back into the oceans. The ratio acts like a thermometer stretching back hundreds of thousands of years. Our era will show a sharp warming spike unlike anything in recent geological history. The warming is happening too fast to be explained by orbital changes or solar cycles. It matches perfectly with the carbon isotope anomaly, showing a connection between carbon release and temperature rise. Ocean chemistry leaves its own traces. When carbon dioxide dissolves in seawater, it forms carbonic acid. Lowering the pH, this process is called ocean acidification, and it is happening now at rates not seen in millions of years. Acidic water dissolves calcium carbonate, affecting marine organisms that build shells and skeletons. The fossil record will show a sudden decline in calcifying organisms. During our time period, coral reefs will appear stressed or missing in tropical sediments. Coccolithophores, tiny plankton that make calcium plates, will show reduced calcification or population crashes. These biological changes will line up with the carbon isotope shift and the temperature spike, creating a multi-proxy signature that screams industrial activity. Nitrogen isotopes provide another marker. Modern agriculture depends on synthetic fertilizers made through the Haber-Bosch process, which converts atmospheric nitrogen into ammonia. Natural nitrogen fixation happens through bacteria in soil and plant roots, but it cannot support the crop yields needed to feed 8 billion people. We manufacture about 200 million tons of synthetic nitrogen fertilizer each year. This nitrogen has a distinctive isotope signature because it comes from atmospheric nitrogen rather than biological sources. When extra fertilizer washes into rivers and oceans, it changes the nitrogen isotope ratios in sediments. A future geologist studying nitrogen isotopes in lake and ocean sediments from our era would see unusual spikes linked to agricultural runoff. Then there is plastic. Plastic is maybe the most long-lasting marker of human civilization. We produce about 400 million tons of plastic each year. Much of this ends up in the oceans, where it breaks into microparticles that settle into sediments. Plastic is made from petroleum, which gives it unusual chemical properties compared to natural organic compounds. The polymers are synthetic, meaning they do not occur naturally. Their molecular structures are designed by humans for specific purposes. When buried in sediment and compressed over millions of years, these polymers will leave detectable traces, not intact plastic objects. Those will break down, but the molecular fingerprints will last as unusual hydrocarbon signatures in the rock. Studies of ocean sediments show plastic buildup increasing rapidly since the 1950s. The Great Pacific Garbage Patch is just the visible surface expression. Below the surface, microplastics are falling down constantly, building up in deep ocean basins. When those sediments turn into rock, they will contain a plastiglomerate layer marking our time period. This layer will be thin, maybe only a few centimeters thick after compression, but chemically distinctive. Future analysts using chromatography or spectroscopy would identify synthetic polymers that could only have been made by an industrial process. Radioactive isotopes add another layer. Nuclear weapons testing between 1945 and 1963 released large amounts of radioactive material into the atmosphere. Isotopes like carbon-14, plutonium-239, and cesium-137 spread worldwide and fell to Earth with rain. These isotopes do not occur naturally in significant amounts. Carbon-14 is produced by cosmic rays in the upper atmosphere, but nuclear testing temporarily doubled its concentration. Plutonium-239 does not exist naturally at all on Earth's surface. It is made only in nuclear reactors or weapons. Finding these isotopes in sediments from our era provides clear proof of nuclear technology. The radioactive signature will fade over time because of decay, but it will stay detectable for millions of years. Plutonium-239 has a half-life of 24,000 years, meaning it will be measurable for several 100,000 years. Even after most of the radioactivity decays away, mass spectrometry can detect the decay products and identify their source. A future civilization studying our sediment layers would find isotope ratios that cannot be explained by any natural process. They would conclude that something unusual happened during this time period, something involving high-energy nuclear reactions. Heavy metals provide more subtle signatures. Industrial activity concentrates metals in certain places. Mining operations extract ores and leave behind waste piles with unusual metal amounts. Smelting facilities release metal dust into the air that settles into nearby soils and sediments. Urban areas build up lead from old pipes and paint. Electronic waste contains rare earth elements in combinations that do not occur naturally. These metal signatures will last in the geological record as unusual concentrations that need explanation. Lead isotopes are especially revealing. Lead has 4 stable isotopes with different amounts depending on the source. Lead from ore deposits has 1 isotope mix. Lead from coal burning has another. Lead from gasoline additives has yet another. By analyzing lead isotope ratios in sediments, future geologists could separate natural lead sources from industrial contamination. They could even identify different industrial processes based on the exact ratios present. Concrete adds its own marker. Modern concrete is made from limestone, clay, and sand mixed with certain additives and heated to high temperatures. The resulting material has a distinctive mineral composition, featuring calcium silicate hydrates that do not form naturally in large amounts. When concrete structures crumble and erode, they add these unusual minerals to sediments. The amounts will be highest near former urban centers, but detectable globally because cement dust spreads by wind. A chemist studying sediment composition from our era would identify unusual calcium to silicon ratios, suggesting large-scale artificial mineral production. The combination of all these markers creates what geologists call the Anthropocene signal. The term Anthropocene refers to the proposed geological epoch defined by human impact on Earth systems. Whether it becomes an official epoch is still debated, but the chemical signature is undeniable. Future stratigraphy will show a boundary layer marking the shift from the Holocene to the Anthropocene. This boundary will be marked by simultaneous changes in carbon isotopes, nitrogen isotopes, temperature proxies, ocean chemistry, plastic abundance, radioactive isotopes, metal concentrations, and concrete minerals. The clustering of so many anomalies in a single narrow time interval will be hard to explain through any natural mechanism. But here is the critical insight. All these markers require careful testing to detect. They are not obvious. They do not jump out at you when you look at a rock core. You have to look for them on purpose using the right tools. Carbon isotope testing needs mass spectrometry. Plastic detection needs chemical extraction and identification. Radioactive isotope detection needs specialized equipment and long counting times. Metal concentration mapping needs systematic sampling and careful interpretation. A quick survey would miss most of these signatures completely. This has huge implications for searching for ancient civilizations. If we are leaving markers that need advanced testing to detect, then ancient civilizations would have left similar markers that we have not found because we have not looked correctly. The absence of detected signatures does not mean signatures do not exist. It means we need better search plans and more systematic studies of ancient sediments. The fingerprints are in the stone waiting to be found. We just need to build the forensic tools to read them. The urgency becomes clear when you think about time scales. Our industrial civilization has lasted about 300 years so far. Optimistically, it might continue for a few more centuries before shifting to sustainable energy sources or collapsing under environmental stress. That gives us maybe 500 to 1,000 years of intense industrial activity total. In geological terms, this is a blink. A layer representing 1,000 years would be millimeters thick in typical sediment deposits. Finding such a thin layer in ancient rocks and separating it from natural variation requires precision we are only beginning to build. But the layer exists. We are creating it right now. And if others created similar layers in the past, they are out there somewhere in the rocks waiting for someone to look in the right place with the right tools. 56 million years ago, something went catastrophically wrong with Earth's climate. Within a few thousand years, global temperatures spiked by 5 to 8 degrees C. The Arctic Ocean reached 20 degrees C, warm enough for comfortable swimming. Antarctica, currently a frozen wasteland, supported subtropical forests. Palm trees grew in Alaska. Crocodiles lived near the poles. The event lasted between 150,000 and 200,000 years before temperatures gradually returned to earlier levels. Scientists call it the Paleocene Eocene Thermal Maximum, abbreviated PETM, and it represents one of the most dramatic and mysterious climate events in recent geological history. The PETM was not the hottest period in Earth's history. The planet has been much warmer during other eras, but the PETM stands out because of how fast the warming happened and because of the chemical signatures linked to it. When geologists examine sediment cores spanning this period, they see something that looks eerily familiar to anyone studying modern climate change. Carbon isotope ratios shift dramatically toward values showing a massive release of organic carbon. Ocean chemistry changes in ways consistent with acidification. Deep-sea organisms suffer mass extinction. Temperature proxies spike sharply upward. The pattern matches almost exactly what human civilization is creating right now, just spread across longer time scales. The mystery begins with the carbon, something injected between 2,000 and 7,000 gigatons of carbon into the atmosphere during the start of the PETM. For comparison, humans have released about 500 gigatons since the Industrial Revolution began. The PETM carbon release was huge, and it happened relatively quickly by geological standards. The isotope composition of this carbon shows clear depletion in carbon-13, meaning it came from organic sources rather than volcanic emissions. But identifying the exact source has been difficult. Volcanoes are the usual suspect for rapid carbon release, but volcanic carbon does not match the isotope signature observed. The carbon came from somewhere else. Several ideas try to explain the PETM. The most popular involves methane hydrates, ice-like structures formed when methane gets trapped in frozen sediments under high pressure. Vast amounts of methane hydrate exist today in ocean sediments and permafrost. If something triggered the release of this methane, either through warming oceans or destabilized sediments, it could have produced the observed carbon spike. Methane is organic in origin, made from decomposing organisms, so it carries the depleted carbon-13 signature. Once released into the atmosphere, methane turns into carbon dioxide within decades, creating long-lasting warming. The theory is plausible and explains most observations, but it has problems. Triggering enough methane release to explain the warming requires an initial warming pulse to destabilize the hydrates. What caused that initial pulse? Some researchers suggest volcanic activity under the North Atlantic as Greenland separated from Europe. The volcanism could have heated ocean sediments, releasing methane, which amplified the warming and released more methane in a runaway feedback loop. Others suggest orbital changes that increased solar heating in key regions. The trigger remains unclear, and the exact timeline is hard to rebuild from the geological record. Here is where it gets interesting for the Silurian hypothesis. The PETM carbon isotope excursion looks very similar to what an industrial civilization would produce. The depletion in carbon-13 matches what you would expect from burning fossil fuels. The timing, while spread over thousands of years, happens rapidly by geological standards, faster than most natural carbon cycle disruptions. The related environmental changes, including warming, ocean acidification, and ecosystem disruption, mirror the effects of human-caused climate change. If you did not know the PETM happened 56 million years ago, before primates existed, You might suspect industrial activity as the cause. Schmidt and Frank studied the PETM closely because it is the best possible example of an ancient industrial-like event. They asked whether the isotope and temperature data could separate a natural catastrophe from an artificial one. The answer is unclear. The PETM isotope spike rises and falls over a few 100,000 years. Human carbon emissions are happening over a few 100 years, 1,000 times faster. This speed difference should be detectable in high-resolution sediment cores. But getting high enough resolution to separate events lasting thousands of years from events lasting hundreds of years requires exceptional preservation and careful work. Most PETM cores do not have enough resolution to rule out a faster initial pulse. Imagine a civilization that lasted 10,000 years and burned fossil fuels the whole time. The carbon isotope signal from that civilization would appear in sediments as a sharp spike if you had century-scale resolution. But compress that sediment over millions of years, lose some material to erosion, average out local differences, and the spike smears into a broader signal that seems to last tens of thousands of years. Without extremely high-resolution sampling, you could not separate it from a natural pulse. The PETM cores we have show a signal lasting tens of thousands of years at least, but they lack the resolution to tell whether a sharper pulse existed within that window. The environmental impacts of the PETM support both natural and industrial interpretations. Deep ocean temperatures rose dramatically, showing the warming was global and affected the entire ocean circulation system. Species living in the deep sea suffered mass extinction, especially organisms that built calcium carbonate shells. The extinction pattern matches what you would expect from ocean acidification combined with warming and oxygen depletion. Surface ocean organisms experienced major turnover, but not total extinction, adapting to new conditions over thousands of generations. On land, many mammal groups suddenly appeared or diversified, including early primates. Ecosystems changed completely during and after the PETM. These changes could come from natural climate forcing. Methane release combined with orbital variations and possible volcanic carbon dioxide could have driven the warming. Ocean circulation changes triggered by warming high-latitude waters could have reduced deep ocean oxygen and created the observed extinction pattern. The ecosystem turnover could have resulted from climate zones shifting and creating new ecological opportunities. Every observation has a natural explanation that fits the data reasonably well, but every observation also fits an industrial explanation. Yeah, a civilization releasing carbon would warm the planet. The warming would change ocean circulation and chemistry. Species would go extinct or adapt. Ecosystems would transform. The two scenarios produce results that look the same in the geological record. The PTM was not the only hypothermal event. Several smaller warming pulses happened in the millions of years following the PM, including one especially mysterious event called the Eocene layers of mysterious origin. This event shows similar carbon isotope anomalies and warming signals, but on a smaller scale. The cause is even less clear than for the PTM. Some researchers suggest additional methane releases. Others point to volcanic activity. The pattern suggests Earth's climate system was unstable during this period, ready for sudden shifts triggered by relatively small perturbations. Or maybe something else was happening that we do not fully understand. Ocean anoxic events from earlier times show similar features. During the Cretaceous period, about 90 to 120 million years ago, the oceans went through multiple episodes where deep waters lost their oxygen and became toxic to most life. These anoxic events lasted for hundreds of thousands to millions of years. They left distinctive black shale deposits rich in organic carbon that was preserved because decomposition needs oxygen. The carbon isotope ratios during these events show anomalies similar to the PETM, though usually less extreme. The causes are debated, but most ideas involve some combination of volcanic activity, ocean circulation changes, and nutrient runoff triggering massive algae blooms that used up oxygen. Could any of these events have industrial causes? The timing is awkward. The Cretaceous anoxic events happened when dinosaurs dominated the land. The PEM happened when mammals were small and primitive. Neither period had obvious candidates for intelligence and technology. But not finding candidates in the fossil record does not prove candidates did not exist, especially for rare species that might not fossilize. The events themselves are suspicious because they show carbon release patterns that look more like human activity than any natural mechanism we fully understand. Natural explanations exist for each event, but none of those explanations are completely satisfying. Each one needs some combination of unlikely triggers and feedback loops that just happen to produce the observed results. The PETM especially bothers researchers because of its speed. While the carbon release happened over thousands of years rather than centuries, that is still extremely fast by geological standards. Natural carbon cycle disruptions usually happen over hundreds of thousands to millions of years, as tectonic processes and weathering slowly move carbon between reservoirs. Sudden releases need special circumstances. Methane hydrate destabilization is one of the few natural mechanisms that could act quickly enough, but it needs an initial trigger that is still mysterious. Without a clear triggering mechanism, the chance of another explanation stays open. Here is what we know with confidence. The PEP happened. Something quickly injected massive amounts of organic carbon into the atmosphere. Temperatures rose sharply. Oceans acidified, species went extinct, ecosystems transformed. These are facts supported by multiple lines of evidence from places around the world. What we do not know is exactly what caused the carbon release or why it happened when it did. The standard methane hydrate hypothesis gives a framework, but gaps in the explanation leave room for doubt. Now consider the implications. If a previous civilization caused the PET, they probably did not survive it. The warming would have destroyed their agricultural systems, disrupted their infrastructure, and caused cascading failures across their society. The event lasted long enough that any civilization would have collapsed under the sustained environmental stress. Their physical artifacts would have completely eroded away by now. Their only remaining trace would be the carbon isotope anomaly and its related climate impacts, which is exactly what we observe. The evidence fits, but the evidence also fits natural explanations. This is the central problem with the Silurian hypothesis. You cannot clearly tell the difference between scenarios when both make similar signatures and the physical evidence that would separate them has been destroyed. We are left with uncertainty and uncomfortable questions. The PTM could have been natural. It probably was natural, but we cannot prove it was natural. And the chemical fingerprints look suspiciously like what we would expect from an industrial civilization burning through fossil fuel reserves before collapsing under the weight of its own emissions. The PEM serves as a warning no matter what caused it. Whether triggered by methane hydrates, volcanic activity, or a hypothetical ancient industry, the event shows what happens when massive amounts of carbon enter the atmosphere quickly. The planet warms sharply, oceans acidify, species go extinct, ecosystems collapse and reform into new configurations. These are not theoretical projections. They happened 56 million years ago, leaving clear evidence in the rocks. The same processes are beginning now as human civilization releases carbon at unprecedented rates. We are running a real-time experiment in rapid climate change, and the PTM shows us one possible outcome. The planet survived. Many species did not. Whether human civilization will survive remains an open question that the geological record cannot answer yet. Human civilization is 300 years old. Not human beings, not even human culture, but industrial civilization, the kind of human society that burns fossil fuels and builds factories and transforms the planet, has existed for about 3 centuries. Before that, we were agricultural. Before agriculture, we were hunter-gatherers. Before anatomically modern humans, we were earlier hominids using stone tools. Trace the lineage back far enough, and you reach primates who lived in trees and had no technology beyond, sometimes using sticks to fish for insects. The whole story of human technological development from the first stone tools to nuclear reactors spans maybe 3 million years. Industrial civilization itself is a tiny fraction of that timeline. A brief explosion of activity that began around 1750 and continues today. Now consider the bigger picture. Complex life on Earth, meaning multicellular organisms more advanced than algae, has existed for at least 600 million years. Land animals have existed for about 400 million years. Vertebrates with large brains and complex behaviors have existed for over 300 million years. The timeline is huge. The opportunities for intelligence to evolve are many. Yet, human civilization takes up only the last 0.1% of that timeline. We are a recent arrival, newcomers to a planet that has already seen billions of years of evolution. The assumption that we are the first and only technological civilization to appear during those billions of years starts to look less like certainty and more like unjustified confidence. The math is uncomfortable. If technological civilizations are even somewhat possible given the vast timeline available, you would expect multiple cases over hundreds of millions of years. Intelligence evolves easily in lineages that face the right selective pressures. Tool use appears in multiple groups. Social complexity shows up in many forms. Language and culture are not unique to humans. The ingredients for technological development have existed many times before us. Yet we assume none of those cases cross the threshold into industrial civilization simply because we see no evidence. But as we established, evidence would not necessarily survive. Think about the life cycle of a civilization. Human industrial society has lasted 300 years and faces serious challenges from climate change, resource depletion, and environmental degradation. Optimistically, we might switch to sustainable systems and continue indefinitely. Pessimistically, we might collapse within the next few centuries, unable to manage the consequences of our rapid growth. Let us assume, for the sake of argument, that industrial phases are naturally unstable and short-lived. They burn through accessible resources quickly, destabilize their environment, and then either collapse or shift to something more sustainable that leaves fewer traces. How long might such a phase last? 10,000 years would be remarkably long. 1,000 years seems more plausible. 100,000 years would be extraordinary. Now run that scenario across 400 million years of complex land life. How many chances exist for a short-lived industrial civilization to rise and disappear? Thousands, maybe tens of thousands if conditions were right many times. Each civilization would last long enough to change its environment, leave chemical signatures and sediments, and then vanish as geological processes erase the physical evidence. The signatures would be scattered through time, buried in different rock layers, limited to different regions. Finding any specific signature would require knowing exactly when and where to look. Missing all of them would be easy if you were not searching systematically. Here is the central insight of the timeline problem. The longer the overall timeline and the shorter the industrial phase, the more difficult detection becomes. Imagine trying to find a 1 cm layer in a rock sequence that is 10 km thick. You would need to examine every layer carefully. Most geological surveys do not work that way. Geologists sample representative sections, examine interesting features, and estimate broader patterns. A thin, unusual layer could be missed completely if it is not exposed in convenient places or if samples happen to skip over it. The chance of detection drops as the target becomes smaller and more localized in time and space. Human industrial civilization might last 500 years total at high intensity. That is 500 years out of 400 million years of opportunity. The ratio is 0.0125%. If another civilization existed for a similar length 100 million years ago, it took up 0.05% of the time between then and now. The signal would be extremely brief in geological terms. Sediment cores usually resolve events on the scale of thousands to tens of thousands of years. Events lasting hundreds of years might be squeezed into single samples. Telling them apart from background variation takes luck and high-resolution analysis. The fossil record shows this problem clearly. Paleontologists have identified maybe 250,000 fossil species from Earth's whole history. Estimates for the total number of species that ever lived range from 5 billion to over 20 billion. We have fossils for maybe 0.01% of species. The vast majority left no trace. This is not because they were unimportant or rare. Fossilization is just an unlikely process. Most organisms decompose without leaving remains that can turn into fossils. Most environments do not preserve fossils. Also, most fossils that form get destroyed by geological processes before they are found. The incompleteness is staggering. Now apply that logic to civilizations. A species becomes technological. It builds cities and factories. It uses resources. It lasts for 10,000 years, which is 20 times longer than human industrial civilization has existed so far. Then it collapses or transitions. Over the next few million years, its cities erode completely. Its metal artifacts rust away. Its plastics break down into smaller molecules. The only traces are chemical signatures in sediments and maybe some disturbed stratigraphy where mining happened. How many such civilizations could have existed and left traces we would never find without deliberate searching? The answer is probably many. Consider a specific example. Suppose a civilization arose during the late Cretaceous period, around 70 million years ago. They existed for 50,000 years in a region covering about the area of modern North America. They mined coal and metal ores, built cities, changed their local environment, and eventually collapsed due to climate change they caused. After their collapse, erosion and geological processes began erasing the physical evidence. 50,000 years of civilization compressed into a sediment layer only a few meters thick at most. Over the next 70 million years, that layer got buried under hundreds or thousands of meters of newer deposits. Tectonic activity folded and faulted the rock. Erosion exposed some sections in cliffs and canyons. Other sections stayed deeply buried. What are the odds that we would find evidence of this civilization? First, we would need to survey rocks of the right age, which we do for other reasons, but not systematically everywhere. Second, we would need to sample the exact layers holding the civilization's signatures, which is unlikely if we are looking for dinosaur fossils or petroleum deposits instead of industrial traces. Third, we would need to analyze samples with methods able to detect unusual isotopes and synthetic compounds, which almost never happens because it is not standard practice. Fourth, we would need to recognize anomalies as meaningful rather than dismissing them as contamination or natural variation. The chance of success at each step is low. The combined probability becomes extremely small. Yet this hypothetical civilization would be real in this scenario. It existed. It left traces. And those traces remain in the rock if you knew where to look and what methods to use. The absence of detection does not mean the civilization was absent. It means we are not searching the right way. This is the timeline problem in its purest form. The longer Earth's history, the more chances for civilizations to arise. The shorter their industrial phases, the harder they are to detect. Our failure to find evidence is not evidence that they failed to exist. The Drake equation used to estimate the number of communicating alien civilizations in the galaxy includes a term for the lifespan of technological civilizations. This term, usually called L, has enormous effect on the final calculation. If civilizations last millions of years, the galaxy might contain thousands of active civilizations at any given time. If civilizations last only thousands of years, the galaxy might contain 0 or 1. The difference between a common universe full of intelligence and a rare universe where we are alone depends mostly on how long civilizations last. The logic applies to Earth's history. If industrial phases last millions of years, we should find evidence easily. If they last thousands of years, we might never find anything. The unsettling idea is that industrial civilization might be naturally unstable. The shift from pre-industrial to industrial unlocks huge energy resources that enable rapid population growth and technological development. But the same resources, when depleted, create crisis. Fossil fuels are finite. Easily accessible minerals get used up. Agricultural productivity has limits. Waste builds up. Climate destabilizes from emissions. The system that enabled rapid growth contains the seeds of its own collapse. Every civilization following this path faces the same limits. The physics and chemistry are universal. The timeline from industrial revolution to crisis might be surprisingly similar across different species, because it is set by planetary resources and thermodynamic limits, not cultural factors. If this pattern holds, then Earth might have hosted dozens of industrial civilizations, each lasting a few thousand years before collapsing. Each would have left chemical signatures in local sediment deposits. Each would have been separated from the others by millions of years, long enough for the planet to recover and evolution to produce another intelligent species. The signatures would be scattered through the geological record like pages torn from a book and buried in different places. Reading the full story would require putting together fragments from widely separated sources, most of which we have never examined. Human civilization sits at a critical moment. We have had industry for 300 years. We face growing environmental pressures. The decisions we make in the next century will decide whether we become a long-lived, sustainable civilization or another brief pulse in Earth's history. If we collapse, future intelligent species might study our chemical signatures millions of years from now and wonder what happened. They might develop their own Silurian hypothesis and debate whether we were natural or artificial. They might never find final proof because we existed too briefly and too long ago for clear detection. We would become a mystery, an uncertain anomaly in the geological record, possibly one of many. The timeline problem has no solution. We cannot survey all rocks from all periods with enough resolution to rule out ancient civilizations. The task is too big and the resource is too limited. We can only sample when we get opportunities and hope to find something obvious. The absence of obvious findings tells us almost nothing about true absence. It tells us only that if civilizations existed, they were not obvious. And as we have seen, there is no reason to expect them to be obvious. The evidence would be subtle, local, and easy to miss. The timeline is huge. The industrial phase is brief. The chance of overlap between where we look and where evidence exists is therefore small. We might be surrounded by traces of past civilizations and never know simply because we have not looked in the right places with the right methods. The timeline problem guarantees uncertainty and ambiguity. It leaves the question permanently open. If you wanted to find evidence of an ancient industrial civilization, where would you look? The question is not rhetorical. It needs specific answers based on what we know about preservation, accessibility, and detectability. The search cannot be random. Earth's geological record is too huge and too fragmentary for random sampling to work. You need a strategy that maximizes the chance of finding signatures while minimizing the resources required. That strategy begins with understanding which environments preserve chemical traces and which places expose rocks from important time periods. Ocean sediments offer the best preservation. The deep ocean floor builds up sediment continuously at rates of a few centimeters per 1,000 years. The environment is stable, protected from erosion, and relatively undisturbed by biological or geological activity. Chemical signatures laid down in ocean sediments can stay intact for hundreds of millions of years until those sediments either get subducted or lifted into mountain ranges. The problem is access. Most ocean sediments stay underwater, requiring expensive drilling operations to sample. Ocean drilling programs have collected cores from thousands of places over the past 50 years. But those cores were collected for specific research goals like understanding climate history or finding oil deposits. Few, if any, were analyzed specifically for industrial signatures. The International Ocean Discovery Program keeps a library of sediment cores covering much of Earth's history. These cores sit in storage facilities, cataloged and available for research. Examining them for unusual isotopic ratios, synthetic compounds, or metal anomalies would be straightforward with modern analytical methods. The work would be tedious and time-consuming, requiring systematic sampling of cores from different time periods and places. But it is technically possible. Nobody has done it systematically because the assumption has been that nothing is there to find. The Silurian Hypothesis changes that assumption. Those cores might contain exactly the evidence we need, waiting to be analyzed with the right questions in mind. Lake sediments provide another promising target. Ancient lakes sometimes left thick sediment deposits that survived later geological activity. The Green River Formation in Wyoming, Utah, and Colorado is maybe the best-known example, containing exceptionally well-preserved fossils and organic remains from about 50 million years ago. The sediments formed in large lakes that lasted for millions of years, building up fine-grained material that captured detailed records of the environment. Similar lake deposits exist from many time periods around the world. These deposits often contain high-resolution records because lake sedimentation rates can be much faster than ocean sedimentation. Events lasting centuries or even decades might be preserved as distinct layers. Searching lake deposits means identifying formations from specific time periods and analyzing them for industrial signatures. Nitrogen isotopes would show fertilizer use. Carbon isotopes would show fossil fuel burning. Metal concentrations would reveal mining or smelting. Synthetic organic compounds would show chemical manufacturing. The methods exist. Applying them systematically to ancient lake deposits would take years and major funding, but it would give clear answers about whether industrial activity happened during those times. The fact that this work has not been done tells you something about scientific priorities and assumptions. When you do not expect to find anything, you do not look. Ice cores offer unique advantages but serious limits. Antarctic and Greenland ice cores provide detailed climate records going back 800,000 years. The ice preserves atmospheric samples in tiny bubbles, allowing direct measurement of past carbon dioxide levels, methane concentrations, and isotopic ratios. If an industrial civilization existed during the past million years, ice cores would show clear evidence. The problem is that ice cores only cover the recent past. Earth's ice sheets are geologically young. Old ice has either melted or been compressed and deformed beyond usefulness. Any civilization older than about 2 million years cannot be detected through ice cores because the ice from that time no longer exists. This puts a hard limit on ice core-based searches. The method is powerful but limited to very recent geological time. Since complex life has existed for 600 million years and land animals for 400 million years, ice can only survey the most recent 0.5% of the relevant timeline. The odds that a previous civilization happened to exist during that narrow window are low. Ice cores are probably useless for finding ancient civilizations, though they provide valuable confirmation that no industrial activity happened during the relatively recent past. Exposed rock formations provide the most accessible search targets. Anywhere erosion has cut through layered sedimentary rocks, creating cliffs, canyons, or mountainsides with visible layers, geologists can sample systematically across time. The Grand Canyon exposes rocks spanning nearly 2 billion years. The Badlands of South Dakota show 75 million years of sedimentation. The White Cliffs of Dover display Cretaceous chalk deposits. These locations, and thousands like them, offer chances to collect samples from specific time periods without expensive drilling. The challenge is that exposed formations are biased toward certain ages and regions. Not all time periods are represented in accessible outcrops. Analyzing exposed formations for industrial signatures requires adapting existing methods. Geologists already collect samples for many purposes, studying everything from fossil content to mineral composition to magnetic properties. Adding isotopic analysis and synthetic compound screening to standard sampling protocols would be relatively easy. The main obstacle is convincing researchers that the search is worth the effort. Scientific funding follows established priorities. Proposing to search for ancient civilizations triggers skepticism. The work might get dismissed as speculative or pseudoscientific unless framed carefully as a study of detectability limits and false positive rates in isotope geochemistry. One promising approach involves examining known climate anomalies. Events like the PETM already attract research attention because they represent dramatic environmental changes with unclear causes. Studying these events with the Silurian Hypothesis in mind would involve using the full set of industrial signature detection methods. Look for carbon isotope spikes that exceed natural variation. Measure nitrogen isotopes for fertilizer traces. Screen for synthetic organic molecules. Map metal distributions. If an ancient civilization caused or contributed to any of these events, the evidence should be detectable with careful enough analysis. The Cretaceous oceanic events offer similar opportunities. These events occurred about 90 to 120 million years ago when ocean oxygen levels dropped sharply, causing mass extinctions of marine species. The events lasted hundreds of thousands of years and left distinctive black shale deposits rich in organic carbon. The causes remain debated, usually linked to volcanic activity and ocean circulation changes. But the rapid carbon release and environmental disruption mirror modern industrial impacts. Examining these deposits specifically for industrial signatures would test whether any part of the events had artificial origins. Rare earth element distributions provide another possible marker. Modern technology uses rare earth metals widely in electronics, batteries, and magnets. Mining operations concentrate these elements in specific places. Natural rare earth deposits exist, but usually at lower concentrations. Finding unusually high rare earth element concentrations in ancient sediments, especially if the distribution patterns suggest extraction and processing, would indicate possible industrial activity. The search would need systematic geochemical surveys of sediment formations, looking for statistical anomalies that cannot be explained by natural geological processes. Sediment fabric analysis could reveal mining operations. When humans extract ores or excavate large volumes of material, we disturb the natural layering and structure of sediments and rocks. The disturbance creates patterns visible in thin sections under microscopes. Natural sediments show consistent grain sizes, orientations, and layer boundaries determined by hydrodynamic sorting and depositional processes. Disturbed sediments show irregular mixing, unusual particle orientations, and disrupted layering. These features might persist in rocks that were sediments when the disturbance happened. Finding them in ancient formations would suggest large-scale excavation, though telling mining apart from natural landslides or debris flows would be challenging. Biomarker molecules offer chemical fingerprints of life. Certain organic molecules are produced only by specific kinds of organisms. Petroleum contains biomarkers from ancient marine algae and bacteria. Coal contains markers from land plants. When we burn fossil fuels, we release these biomarkers into the environment along with combustion products. Future sediments will contain unusual combinations of ancient biomarkers mixed with modern organic matter. Finding similar combinations in ancient sediments, where biomarkers from different geological periods appear together in the same layer, might suggest fossil fuel combustion by a previous civilization. The search strategy must be systematic and use many approaches. Ocean sediment cores for broad temporal and geographic coverage, lake deposits for high-resolution local records, exposed formations for access and cost-effectiveness, climate anomalies for focused investigation of suspicious events, rare earth surveys for technology traces, sediment fabric analysis for mining evidence, biomarker studies for fuel use signatures. No single method will give final answers. The strength comes from multiple independent lines of evidence either coming together or failing to come together on industrial signatures. Funding remains the main obstacle. The work would require millions of dollars and years of effort from teams of researchers. Convincing funding agencies to support a search for something most scientists think does not exist is difficult. The work must be framed as pure research into detectability limits. Developing methods that could apply to searching for industrial activity on exoplanets or understanding false positives in climate reconstructions. The findings would evaluate whether or not ancient civilizations are found. If the search returns negative results, it strengthens our confidence that we really are first. If it returns positive results, it revolutionizes our understanding of life on Earth. The methods exist. The locations are known. The techniques are available. What is missing is motivation and resources to run systematic searches. The Silurian Hypothesis has opened the door by showing that the question is scientifically legitimate. Now someone needs to walk through that door with proper funding and commitment to follow the evidence wherever it leads. The rocks are waiting. The cores are in storage. The formations are exposed. The chemistry is stable. All that is missing is the will to look seriously for traces of those who might have come before us. Earth destroys its history, but not every world forgets so easily. Two celestial bodies within easy reach of our current technology preserve records that would be impossible to keep on our active planet. The Moon and Mars lack the geological processes that erase evidence on Earth. No atmosphere means no wind erosion. No plate tectonics means no subduction. No liquid water means no weathering. Objects placed on their surfaces billions of years ago would remain mostly unchanged, waiting to be discovered by future explorers. If a previous Earth civilization achieved spaceflight, their artifacts might still exist in near-perfect condition on these neighboring worlds, while every trace on Earth has vanished. The Moon is a museum. Since its formation about 4.5 billion years ago, the lunar surface has been changed only by meteorite impacts and the slow buildup of micrometeorite dust. The rate of change is extremely slow compared to Earth. A footprint left in lunar regolith would remain visible for millions of years before micrometeorite bombardment slowly erases it. A structure built from lunar materials would last basically forever unless directly hit by an impactor. The Apollo. Landing sites look almost the same today as they did in 1969. 50 years have produced no measurable change. In 50 million years, those sites will still be recognizable, though covered by a thin layer of accumulated dust. Now imagine a previous civilization reached the Moon millions of years ago. Maybe they built a base for research or resource extraction. Maybe they left behind equipment, habitation modules, or experimental facilities. Maybe they mined, leaving trenches and disturbed regolith. All of this would remain. The Moon does not erase, it preserves. Anything placed there would become part of the permanent archaeological record, frozen in time, waiting for someone to find it. The search would not be easy. The moon's surface area is about 38 million km, about the size of Africa. Systematic surveying would require high-resolution orbital imaging able to identify unusual features like straight lines, geometric patterns, or unusual albedo variations that might indicate artificial structures. Current lunar orbiters have achieved impressive resolution, with some areas mapped at meter scale or better, but most of the surface has only been imaged at resolutions of 100 m or coarser. Smaller artifacts would be invisible in existing surveys. Recent missions have identified thousands of previously unknown craters, lava tubes, and geological features. Finding artificial objects among the natural clutter would require knowing what signatures to look for. Straight edges, right angles, and right angles. Regular spacing would be obvious indicators. Materials with unusual spectral properties like refined metals or manufactured composites would stand out in multispectral imaging. Local magnetic anomalies might indicate electronic equipment or metal structures. The methods exist. Using them specifically to search for ancient artifacts would require dedicated surveys and careful analysis, but the task is doable with current technology. The far side of the moon offers especially interesting possibilities. The far side always faces away from Earth because of tidal locking. Any civilization launching from Earth would find the far side useful for radio astronomy, since the moon blocks instruments from Earth's electromagnetic noise. A previous Earth civilization might have placed observatories or listening posts on the far side. These facilities would be perfectly preserved and completely invisible to casual observation from Earth. Only dedicated orbital missions have photographed the far side in detail, and those missions were not looking for artificial structures. Mare regions present another interesting target. The lunar maria are large impact basins that later filled with volcanic lava, creating relatively smooth plains. Some maria are over 3 billion years old. If a civilization visited the moon after those lava flows hardened, but millions of years ago, they might have chosen maria for landing sites because of the flat terrain. Artifacts on maria would be easier to spot than those in heavily cratered highlands because the background is less cluttered. Systematic examination of all major maria for unusual features would be a logical first step in searching for ancient lunar evidence. Lava tubes offer protection from radiation and micrometeorite bombardment. These natural tunnels form when lava flows create channels that later drain, leaving hollow tubes. Lunar lava tubes can be enormous, possibly large enough to hold entire cities. A previous civilization that knew about these features might have used them for habitation, creating bases underground where conditions are more stable and radiation exposure is lower. Surveying lava tubes from orbit is difficult because most stay hidden underground. Finding entrance collapses, and using ground-penetrating radar or physical exploration would be necessary to check for artificial changes or artifacts inside. Mars presents different challenges and opportunities. Unlike the moon, Mars has an atmosphere, though thin, and geological processes continue at slower rates. Wind erosion happens slowly. Dust storms move material around. Ancient river valleys and lake beds show evidence of past water flow. The polar ice caps grow and shrink with seasonal cycles. Mars is more active than the moon, but far more stable than Earth. Artifacts placed on the surface millions of years ago would be damaged somewhat, but could stay recognizable depending on place and material. The key advantage of Mars is that it might have been more interesting to a previous civilization. Mars once had liquid water on its surface, a thicker atmosphere, and possibly livable conditions. An advanced civilization exploring their solar system would have studied Mars closely. They might have landed probes, built research stations, or even tried colonization if conditions were right. The artifacts from those activities would last much longer on Mars than similar artifacts would on Earth. Martian sedimentary rocks offer another path for investigation. If a previous civilization visited Mars and left organic material, that material might have been mixed into sediments and preserved as chemical traces or microfossils. The Curiosity and Perseverance rovers have been collecting samples and analyzing Martian rock chemistry. None of their analyses specifically target artificial biomarkers or industrial signatures, because the expectation is that any life on Mars would be microbial and ancient. Reanalyzing data or returned samples with the Silurian hypothesis in mind might reveal missed anomalies. The asteroid belt and outer solar system expand the search space further. If a civilization achieved advanced spaceflight, they might have visited moons of Jupiter or Saturn, mined asteroids, or built facilities on icy moons with subsurface oceans. These places are beyond our detailed exploration right now, but future missions will survey them. Finding artificial structures on Europa or Enceladus would be clear proof of advanced civilization, since natural processes cannot create technological artifacts in those environments. The basic advantage of searching off Earth is that absence of evidence would actually mean something. On Earth, geological processes guarantee that ancient artifacts cannot survive. Not finding them tells us nothing. On the Moon and Mars, artifacts should survive if they existed. Not finding them after systematic searching would strongly suggest they were never there. This difference makes space archaeology potentially more decisive than Earth searches. A positive result would be final. A negative result, after thorough enough surveys, would meaningfully limit the chance of previous spacefaring civilizations. Current space exploration is not designed for this. Lunar missions focus on science and resource assessment. Mars rovers search for signs of ancient microbial life and evaluate future human habitability. Nobody is specifically looking for artifacts from earlier Earth civilizations. Adding that search goal would require only small, extra effort. Orbital imaging already captures high-resolution surface detail. Including artificial structure detection algorithms in image processing pipelines would be straightforward. Surface missions already collect context images. Training personnel to recognize possibly artificial features would take little time. The political and psychological barriers are bigger than the technical ones. Space agencies work under public scrutiny and must justify every decision. Proposing to search for ancient alien artifacts, even if those aliens came from Earth, risks public mockery and funding cuts. The work must be framed carefully as exploration of natural features with incidental attention to anomalies. Only when strong evidence appears can the search be acknowledged openly. Until then, researchers must move carefully to avoid connection with fringe theories and pseudoscience. Some early work has happened quietly. Researchers have examined Apollo landing site images for unusual features. Others have studied high-resolution Mars orbital images looking for regular patterns that might indicate artificial origin. So far, nothing conclusive has appeared, but the surveys have been informal and unsystematic, conducted by individuals rather than organized programs. A proper search would require dedicated missions, systematic protocols, and strict analysis standards. The resources for such an effort could be justified in many ways. Understanding how to detect ancient civilizations helps the search for extraterrestrial intelligence. Developing preservation and detection methods helps plan for our own long-term legacy. And the pure scientific question of whether we are first deserves serious investigation. The Moon and Mars are waiting. They remember everything that touches them. If earlier civilizations reached these worlds, the evidence remains where it was left, unchanged by time, ready to be found. We have the technology to search. We have missions planned. All that is missing is openly admitting that searching for evidence of earlier Earth civilizations is a legitimate scientific goal worth pursuing. The geological record on Earth is uncertain and incomplete. The records on other worlds are clear and lasting. If we want clear answers about whether we are first, we need to look beyond Earth to places where time barely moves and evidence lasts. The artifacts, if they exist, have been waiting for millions of years. They can wait a bit longer until we are ready to search seriously. Here is the twist that breaks everything. The more advanced and sustainable a civilization becomes, the less evidence it leaves in the geological record. A primitive industrial society burning coal and dumping waste makes obvious signatures. Carbon isotope spikes, plastic buildup, metal pollution, synthetic chemicals. The geological fingerprint is clear and distinctive, but an advanced civilization that switches to solar power, recycles materials efficiently, and keeps populations stable leaves almost nothing. Clean energy produces no isotopic anomalies. Perfect recycling removes waste streams. Sustainable agriculture uses minimal synthetic inputs. The paradox is deep. The civilizations most likely to survive long-term are exactly the ones we would never detect. Consider the path of technological development. Early industrial civilization depends on whatever concentrated energy sources are available. For humans, that meant coal, then oil and natural gas. Burning fossil fuels is dirty but effective. The energy density is high. The technology is simple and the resources are abundant at first. Every civilization following a similar path would begin with fossil fuels because they are the easiest high-energy option. This phase makes the biggest geological impact. Carbon pours into the atmosphere. Emissions change chemistry. The signature is unmistakable, but fossil fuels are finite. Eventually, supplies shrink, prices rise, and alternatives become attractive. A successful civilization switches to renewable energy before complete depletion triggers societal collapse. Solar, wind, hydroelectric, geothermal, and nuclear fusion all provide lasting power without producing characteristic waste products. Solar panels turn sunlight directly into electricity with no combustion. Wind turbines pull kinetic energy from air currents. Fusion reactors, if developed, would produce helium as waste, an inert gas that blends into the atmosphere without trace. These technologies leave minimal geological signature compared to fossil fuels. The same pattern applies to materials. Early industry extracts virgin ores, processes them inefficiently, and throws away waste. Metal mining leaves tailings and disturbed landscapes. Smelting releases metals into the environment. Manufacturing creates synthetic compounds. All of this remains in sediments as detectable anomalies. Advanced civilization develops closed-loop recycling where materials cycle again and again through production and use without loss. Need copper. Recycle existing copper instead of mining new ore. Need plastics. Break down old plastics into feedstock and remake them. Perfect recycling removes the need for extraction and minimizes waste generation. Agriculture follows similar logic. Primitive farming exhausts soil and needs continuous synthetic fertilizer input, with its clear nitrogen isotope signatures. Advanced agriculture uses precision methods, maintains soil health, and minimizes outside inputs. Nitrogen gets fixed by engineered bacteria or recycled from organic waste. No extra fertilizer runs off into rivers and oceans. The isotopic signature disappears. An advanced sustainable food system might leave less trace than natural ecosystems. Population control becomes essential for sustainability. Exponential growth cannot continue forever on a finite planet. Every successful long-term civilization must stabilize population at levels their resources can support comfortably. Humans now number 8 billion and rising, stressing resources and creating massive environmental impacts. The civilization that stabilized at maybe 1 billion using sustainable practices would have a much smaller footprint. Fewer people means fewer resources taken, less waste produced, and smaller area of impact. The signature scales with population and consumption. Now consider the implications for detectability. A civilization that exists for 5,000 years in unsustainable industrial mode leaves clear traces. Carbon spikes, plastic layers, metal anomalies. But a civilization that switches after 500 years of unsustainable industry to 500,000 years of sustainable operation leaves a brief spike followed by long periods of minimal impact. The sustainable phase is 1,000 times longer than the industrial phase and becomes invisible in the geological record. You might detect the brief industrial transition, but never realize the civilization continued for 500,000 years afterward. This creates a detection bias. We are looking for signatures of unsustainable industrial activity because those are the signatures we can detect. But unsustainable activity means civilizations heading toward collapse. The evidence we can find represents failure modes. Success modes, where civilizations switch to sustainability and last for geological time scales, are invisible to our detection methods. We might be surrounded by traces of successful civilizations and never know because success looks like absence in the rocks. The paradox extends to artifacts. Durable materials like plastics and metals are useful because they resist decay. But resisting decay creates long-term environmental persistence problems. Successful civilizations probably minimize use of persistent materials in favor of biodegradable alternatives. Buildings might be made from engineered biological materials that decompose when no longer needed. Machines might use recyclable components designed for easy disassembly. Everything is designed for minimal long-term environmental impact. These materials would disappear from the geological record much faster than our current industrial outputs. Technology sophistication matters too. Advanced nanotechnology or biotechnology might allow manufacturing at molecular scales with minimal energy input and zero waste. Computing might use biological materials rather than silicon and rare metals. Transportation might rely on efficient mass transit rather than individual vehicles. Communication might use biological or quantum systems rather than metal infrastructure. None of these technologies would leave obvious geological traces. The more advanced the technology, the lighter the footprint, the harder the detection. Energy efficiency reduces signatures further. Early internal combustion engines converted maybe 20% of fuel energy into useful work. Modern engines reach 30 to 40%. Future engines might reach 80 or 90% efficiency. Perfect engines would turn all input energy into intended work with no waste heat or emissions. An advanced civilization using perfect engines would need far less fuel for the same output, producing proportionally fewer emissions and weaker signatures. Efficiency improvements make civilizations harder to detect. Even space exploration becomes stealthy. Our current approach uses chemical rockets that burn fuel and release exhaust. Future propulsion might use beamed energy, electromagnetic drives, or other methods with minimal exhaust products. Spacecraft might be built from asteroid materials in space rather than launched from Earth. Colonies on other worlds might be entirely self-sufficient, built from local resources with closed ecological loops. Such a spacefaring civilization would leave no launch pads, no rocket exhaust trails, no obvious signs of leaving their planet beyond perhaps some disturbed regolith on airless moons. The sustainability paradox forces us to face uncomfortable possibilities about what advancement really means. We assume advancement means more visible, more powerful, more impactful. But real advancement might mean less visible, more efficient, more blended into natural systems. An advanced civilization might look like a natural ecosystem when viewed through geological lenses. Their cities might be living structures. Their power might come from photosynthesis. Their transportation might use biological movement. Their computing might use organic neural networks. Everything biological, everything recyclable, everything sustainable and completely invisible millions of years later. This has major implications for the search. If we only look for signatures of unsustainable industry, we miss whole kinds of civilizations. The search methods need to grow beyond simple chemical markers to include subtle patterns that might show intelligent management of resources. Ecosystems too stable to be natural, biodiversity patterns too organized to be random, isotopic ratios too consistent to be chance. These would be weak signals needing advanced statistical analysis to detect and interpret, but they might be the only traces left by successful civilizations. The paradox also changes how we judge human civilization's future. We are currently in the loud phase, the unsustainable industrial phase that leaves obvious traces. Our geological signature is forming now and will be detectable for millions of years. But our goal should be to switch to sustainability as fast as possible. Success means becoming quiet. Success means leaving fewer traces. If we achieve that switch and last for millions of years, future geologists studying our era would see a brief industrial spike followed by apparent disappearance. They might think our civilization collapsed when actually it just learned to live within planetary limits. The same applies to any earlier civilizations. If they succeeded, they disappeared from the detectable record by becoming sustainable. We would see only their industrial transition phase as a brief anomaly. Most of their existence would be invisible. This means the absence of evidence for long-lasting civilizations is not evidence they were absent. It is evidence of success. Civilizations that leave clear traces are civilizations that failed to switch. Civilizations that succeeded became undetectable. The rocks preserve failure. Success leaves no mark. This paradox weakens the whole search strategy. If sustainable civilizations are invisible, and only unsustainable civilizations leave traces, then finding nothing after systematic searching tells us only that sustainable civilizations either did not exist or were successful. Finding industrial signatures tells us civilizations existed, but suggests they probably collapsed soon after because unsustainable practices cannot last long. The only way to detect long-lived civilizations would be indirect methods like unusual ecosystem patterns or organized resource management signatures that might show intentional stewardship lasting millions of years. Maybe this is the real message of the Silurian hypothesis. It shows us that the traces we are leaving now are traces of possible failure. The carbon spikes and plastic layers and isotope anomalies are warnings written in stone about what happens when a species industrializes without planning for sustainability. If we want to be truly advanced, we need to become undetectable. We need to shift from loud, destructive industry to quiet, sustainable integration with natural systems. The measure of our success will be how little evidence we leave behind. The civilizations before us, if they existed, might have learned this lesson, or they might have left warning signs in the rocks that we have not yet learned to read. Either way, the paradox stands. Advancement means invisibility, success means silence, and the geological record preserves only the mistakes. The Silurian hypothesis is not really about the past, it is about the future. Every question about whether earlier civilizations existed and collapsed is also a question about whether we will exist and collapse. The geological record might contain warnings written by species that faced the same challenges we face now, or it might contain only silence, leaving us to navigate alone through dangers we cannot fully predict. Either way, the hypothesis forces us to face what our industrial revolution means in the context of deep time and planetary limits. Consider what we know for sure. Earth is 4.6 billion years old. Complex life has existed for over 600 million years. Intelligence has evolved multiple times. Tool use appears across many lineages. We are not unique in thinking or ability. We are unique only in having developed industrial technology that uses fossil fuels at scales large enough to change global systems. That uniqueness might be temporary. It might be our great achievement, or it might be our fatal mistake. The difference depends on decisions we make in the next century. Climate change is not a future threat. It is a present reality. Global temperatures have risen 1.2 degrees C since pre-industrial times. Ice sheets are melting, sea levels are rising, weather patterns are shifting, ocean chemistry is changing. Ecosystems are moving toward the poles. Species are going extinct at rates not seen since the last major mass extinction event. All of this is documented, measured, and undeniable. We are running an experiment in rapid planetary transformation, and the outcomes are still uncertain. The PTM shows what happens during rapid warming. Temperatures rose 5 to 8 degrees over thousands of years. Ocean acidification killed deep-sea organisms. Land ecosystems changed completely. The event lasted over 100,000 years before the planet slowly returned to cooler conditions. Species that could not adapt went extinct. New species evolved to fill empty roles. Life continued, but the biosphere was fundamentally reshaped. Mammals diversified during recovery, taking advantage of ecological opportunities created by the disruption. Our primate ancestors were among the beneficiaries. If the pattern was natural, it shows that rapid carbon release inevitably causes massive environmental upheaval, no matter the cause. The physics and chemistry are deterministic. Add carbon to the atmosphere quickly, temperatures rise. Warm the oceans, chemistry changes. Change chemistry, species die. The chain of cause and effect is unavoidable. If the PMA had artificial parts, if some earlier civilization added to the carbon spike before collapsing, then the event becomes a direct warning. They did what we are doing. They triggered runaway warming. They did not survive. The rocks preserve their failure as a cautionary tale. We cannot prove the PMM was artificial. The evidence is uncertain, allowing both natural and industrial interpretations, but the uncertainty itself matters. It tells us that industrial signatures might be in the geological record, and we simply cannot separate them from natural events. This possibility should terrify us. We might be walking a path already taken by others. We might be repeating mistakes that destroyed earlier attempts at technological civilization. And we have no way to know for sure because the evidence was destroyed or is too subtle to detect clearly. The sustainability question becomes essential. Every civilization faces the same energy transition problem. Fossil fuels enable rapid growth, but run out quickly and destabilize climate. Renewable energy allows sustainability, but requires technological skill to build at scale. The switch from fossil to renewable must happen before either resource depletion or environmental damage triggers societal collapse. The window for a successful switch might be narrow. Wait too long and feedback loops become unstoppable. Move too fast and incomplete infrastructure fails under demand. The timing must be exact. Humans are attempting this switch now. Solar and wind capacity is growing quickly. Battery technology improves each year. Electric vehicles spread. Some nations have reached high renewable use, but fossil fuel use keeps growing globally. Carbon emissions keep rising. The gap between what we need to do and what we are doing remains dangerously large. We may have 20 to 30 years to complete the switch before climate feedbacks make the situation unmanageable. The timeline is tight. The outcome is uncertain. Previous civilizations, if they existed, faced the same challenges. They had the same physics, the same chemistry, the same thermodynamic limits. Their fossil fuels burned the same way ours do. Their atmospheres reacted to carbon dioxide the same way. They experienced the same climate feedbacks, the same resource depletion curves, the same social stresses. If they failed to switch in time, they collapsed. Their cities eroded. Their people died or returned to pre-industrial life. Their moment passed, leaving only faint chemical traces in rocks formed over later millennia. The frequency of these collapses matters greatly. If industrial civilizations often arise and collapse every few million years, the pattern suggests something basic about how hard successful transition is. The universe might be full of the ghosts of failed civilizations, species that found fire and tools and fossil fuels, but could not achieve sustainability. Earth might have hosted a dozen or more such failures over the past 400 million years. Each would have been forgotten completely, erased by geological processes unknown to their successors. We would be the latest attempt, possibly heading toward the same fate. Or, if civilizations are rare and ours really is first, then we carry responsibility for proving that technological intelligence can be sustainable. We would be setting the example for what success looks like. Our choices will decide whether industrial civilization can fit within planetary limits or must destroy itself. The weight of that responsibility should shape every decision we make about energy, resources, population, and environmental management. The Drake equation's L term haunts this analysis. L represents the lifespan of technological civilizations. If L is short, measured in centuries or millennia, then civilizations appear and vanish too quickly to overlap in time or space. The galaxy might host billions of technological species over its history, but never more than a few at once. If L is long, measured in millions of years, then civilizations last and might make contact with others. The difference between short and long L decides whether intelligence is common but brief, or rare but enduring. Our own L is unknown. Human industrial civilization has lasted 300 years. Extending that to 1,000 years would be impressive. Reaching 10,000 years would require a successful switch to sustainability and long-term stable governance. Surviving 1,000,000 years would demand technology beyond anything we can currently imagine, along with cultural stability and environmental stewardship at scales beyond human history. Most futures fail long before that point. The chance that we are one of the rare successes is low based only on statistics. The geological record offers no comfort. If earlier civilizations existed and succeeded, they are invisible. If they failed, they left at most uncertain traces we have not clearly identified. Either we are first and must succeed, without guidance, or we are the latest in a series of failures and must break the pattern. Both possibilities put the burden entirely on us. No ancient wisdom will save us. No alien rescue is coming. We face the crisis alone with only our intelligence and cooperation to guide us through. The next century will decide everything. Climate feedbacks are speeding up, tipping points approach. Arctic sea ice disappears in summer. Permafrost thaws, releasing methane. The Amazon rainforest shifts toward savanna. Greenland and Antarctic ice sheets destabilize. Each tipping point crossed makes later warming harder to control. We are racing against exponential processes with linear solutions. Success requires immediate action at scales never before achieved in human cooperation. The alternative is clear. Failure means collapse. Social structures cannot survive long-term environmental chaos. Food production fails when weather becomes unpredictable. Infrastructure crumbles when storms exceed design limits. People migrate when regions become unlivable. Conflicts erupt over shrinking resources. Governments break down under stress. The cascade speeds up until complex civilization becomes impossible to keep. Survivors return to simpler life. Technology is lost. Knowledge fades. The species continues in reduced form. maybe for millions of years, until another lineage or another attempt emerges. If that happens, if we fail and collapse, future intelligent species will study our geological signature. They will see the carbon spike, the plastic layer, the isotope anomalies. They will recognize these as signs of industrial activity. They will debate what happened to us. They will wonder if they might follow the same path. They will develop their own version of the Silurian Hypothesis, searching rocks for evidence of civilizations before them. They will find uncertain traces, too weak to prove but suggestive enough to worry, and they will face the same choices we face now. This cycle might have repeated many times. Each round adds another faint layer to the geological record. Each failure leaves warnings that later species cannot read clearly enough to learn from. The pattern continues until some civilization finally succeeds, making the shift from unsustainable to sustainable, lasting long enough to detect and prevent the next attempt from repeating old mistakes. Or the pattern continues forever. Intelligence arises, industrializes, and collapses in endless repetition across deep time. Earth becomes a graveyard of ambition, littered with chemical ghosts of species that reached for the stars and fell back to dust. We stand at the edge. The path forward splits into success and failure. Success requires unprecedented cooperation, rapid technology deployment, and deep changes to economic systems built for growth instead of stability. Failure requires only continued delay, weak action, and business as usual. The default path leads toward collapse. Success demands active choice and sustained effort. Most of history suggests we will fail, but history is not destiny. Knowing the pattern gives us a chance to break it. The Silurian Hypothesis gives awareness. Awareness that we might not be first, awareness that earlier attempts might have failed, awareness that the rocks might contain warnings we need to heed. Even if those warnings are uncertain, even if we can never prove earlier civilizations existed, the possibility alone should motivate us. We have seen what rapid carbon release does to planetary climate. We understand the feedbacks and tipping points. We know the consequences of doing nothing. The warnings are clear. Even if their source is uncertain, future generations will judge us by the world we leave them. If we succeed in switching to sustainability, they will inherit a planet that can support civilization for geological time scales. If we fail, they inherit chaos, collapse, and the long, painful recovery toward stability. The choice seems obvious, but obvious choices are not always easy choices. Vested interests resist change. Political systems struggle with long-term planning. Economic pressures favor short-term profit over long-term survival. Overcoming these barriers requires a shared will we have not yet shown consistently. The rocks are waiting. They will record our choices faithfully. Carbon isotopes will spike or stabilize. Plastic layers will build up or vanish after production stops. Temperature proxies will show continued warming or successful stabilization. Metal concentrations will mark our mining. Synthetic compounds will last for millions of years. Future geologists will study our layer and decide what we did and whether it worked. We are writing our epitaph in stone right now. The question is whether that epitaph will read tragedy or triumph. The Silurian Hypothesis shows us the stakes. We are not just gambling with our own survival. We are deciding whether industrial civilization is possible long-term or naturally self-limiting. If we fail, we prove that technology and sustainability cannot coexist at planetary scale. If we succeed, we show that intelligence can move past its destructive phase and find balance. The rocks preserve the answer for anyone who comes after, and maybe for anyone who came before. Their warnings still echo faintly in the chemistry of ancient sediments, waiting for us to learn how to listen. The shadow of the future falls across the present. What we do now matters forever.